Okay, now we're going to go on to measuring variability. Lesson 18, we were looking at center. Now we're going to look at variability. So we're going to look at what is a typical value, and now how spread out from that typical value could you describe a distribution. So we'll look at the standard deviation. We'll look at the quartiles and the IQR. We're going to have our 5-number summary. We're going to identify outliers using the 1.5 times IQR rule, and then combine all of these features, or at least the last two, to create a box plot. So the standard deviation, you're going to hear language sometimes like vary on average. And the idea is we want to figure out, on average, like what is a typical deviation from the mean. So here's an observation. How far is it from the sample mean? Here's another. How far is that from the sample mean? So we're going to do that for every single point, that kind of idea. So if we are calculating this for a sample, we're going to use the notation, the letter S. And so each observation minus the sample mean, and then we're going to square that difference. This comes in part because, quite honestly, squaring had nicer features than the absolute value, and back in the day we didn't have the computing power we do now. And then we're going to divide not by n, but n minus 1. And we'll touch on why the n minus 1, like way down the road, but just know it has to do with like a biased estimator, so we have to use n minus 1 and not n. So standard deviation is going to be in the same units that our variable x is in, and as you can see here, it uses the sample mean to calculate the sample standard deviation. So if you have a scenario where you have very skewed data or you have extreme outliers and it impacts the mean, it's also going to impact the standard deviation. So this warning is saying, hey, it's going to definitely be impacted if you have extreme outliers. And that's why. It's pretty much the second the sample mean's bad, your standard deviation is going to be bad as well. So if you have very skewed data or extreme outliers, watch out. It may not be the measure of spread that you want to use. So we're going to come back to this engineering course exam, entrance exam. So we have 5 students, we have their exam scores, and we want to calculate the standard deviation for the exam score. So just as a reminder, x bar, so when you take these 5 values, it should be 82.8 points if you want units. My sample size, they're just 5 students, so I'm going to use that. So just setting up here, my standard deviation is equal to, from 1 to 5, xi minus x bar squared over n minus 1. And that'll be my setup. So just putting this all together, 79 minus 82.8 squared plus 88 minus the sample mean squared plus, I'm going to do the dot dot dot, I don't want to write all 5, but obviously you are welcome to, minus the sample mean squared. I'm implying that I have all 5 there. Oops. Divide that by 5 minus 1. So I end up getting, absolutely give yourself a chance to plug this in. Don't just blindly trust my math. It's always good to check. So after I square root, I end up getting something like, rounding, I have 9.52. If you want units, it'd just be points because it's an exam. So we have an average of 82.8 points on this exam, and the scores vary on average about 9.52 points from that average. So quartiles. they are a special case of percentiles. So specifically at the quarters. So the first quartile is the 25th percentile. We do have okay, so quartiles. The IQR is something that we calculate from the quartiles. So the first quartile right here, it has 25% below that value. The second quartile, which we rarely actually call the second quartile, has 50% below. That is because we call it the median. And then the third quartile, so 3/4, has 75% below. And I mean, you can keep going, like you could say the 0th quartile has 0 below. The fourth has 100% of the data below it, that kind of idea. So when we want to figure out a way to talk about spread using these quartiles, we usually will refer to the interquartile range. So it ends up being the middle 50% of the data, so the third quartile minus the first quartile. So we end up looking here. This is the middle 50% of our data. When we put a box plot together, those are the edges of our box. So absolutely, if you wanted to calculate where the quartiles are, first you find the median. Then for the first half, you're going to find the median for the first half. That's Q1. Find the median for the second half. And that's Q3. That's how we would find them. It's essentially just kind of folding. First you fold the data set in half. Then you take each half and fold that in half. So then we have a 5-number summary that we like to talk about. This is a great way to just kind of quickly summarize, like, hey, where's the center, where's the spread? Absolutely alone, like you're going to want to have a plot that you can look at. You usually want to have data sets that are more than 5. Definitely you don't want to use this for data sets that have fewer than 5. This is pretty useless for data sets that small, but people do it. So it's the minimum, first quartile, median, third quartile, maximum. So we actually use pretty much all these points in our box plot. So Q1, and then our median in Q3, that's our box right there. So things to be cautious though, our min and our max. The whiskers will go out to the highest value that isn't an outlier. And if the max isn't an outlier, it'll go to the maximum. The lower whisker is going to go to the lowest value that is not an outlier. But this right here, this will be the min. So the min is always the lowest value, even if it's an outlier. The max is always the highest value, even if it's an outlier. And how we define outliers, we're going to use this 1.5 times IQR rule. So if we take 1.5 times the IQR, subtract it from the first quartile, any value lower than that is going to be a low outlier. If we take 1.5 times IQR and add it to the third quartile, any point above it is going to be an outlier. So we're going to go ahead, we're going to take a somewhat basic example and calculate the outliers as well as draw the box plot. Okay, so below what we have is a data set. We're looking at commuting times in minutes for 20 randomly selected New York workers. Of course, this would be before working remotely probably, and back when public transit was really, really popular. New York in particular is definitely shut down. So we need to find some information here. So if I have 20 randomly selected workers, that means that if I fold it in half, I think it's right around here. Count, that's 5, 5, 5, 5, yeah. So my median, it's going to be the average of 20 and 25. So it's going to be 22.5. things to note, all of these, they're still going to be in minutes. The min and the max are pretty easy when, in this case, they're already in order. So my min, my max. So my min was 5 minutes. My max was 85 minutes. Now to the quartiles. So I have 10 on each side. And if I split that in half, I'm going to average 15 and 15. Which I like averaging one number with itself. It usually is pretty easy to calculate. So 15 minutes. And then, right, 5 and 5. So then the third quartile, I need to average 40 and 45. It's going to be 42.5. So there we are. Then if I wanted to calculate the IQR, it's also really helpful to have. I'm going to take the third quartile minus the first quartile. If you mix up the order, it's really easy to spot because you shouldn't get a negative number, typically, unless you have some sort of quantitative variable that has negative numbers, but you should not get a negative number ever for the interquartile range. So 42.5 minus 15, what, 27.5 minutes. So that's my IQR. So that's saying the middle 50% of my data set is has a range of 27.5 minutes. So we're going to go ahead and we're going to still build on this in the next slide here. So 27.5 minutes, 15 minutes, and then 42.5 minutes. So we are going to go ahead and put together what are my lower and upper cutoffs for outliers. So I want to figure out, okay, points below this point are going to be low outliers, points above this point are going to be high outliers. So I'm going to start with my lower cutoff. So that'll be Q1 minus 1.5 times IQR. So I'm just going to plug everything in from right here. So 15 minus 1.5 times 27.5. So right off the bat, looking at this, I know this is higher than 15. I know this is going to go negative. But I'm just going to get what, negative 26.25. So unless they have a time machine and it takes a negative time to get to work, which isn't possible to my knowledge, we're basically going to say, okay, well, people who took less than 0 minutes will be a low outlier. If you look, the shortest amount of time it took anybody was 5 minutes. We're not going to have any low outliers, so no low outliers. Then we're going to do our upper cutoff. So that'll be Q3 plus the 1.5 times IQR. So I will get what, 42.5 plus 1.5 times 27.5. Get something like 83.75 minutes. So what this is saying is if I have any commute times above 83.75 minutes, they're going to be an outlier on the high end. So looking here, yes, I do have a high outlier. I have one time of 85 minutes, so that value is higher than this cutoff, so it will be an outlier on the high end. 65 is as high as it gets before I have any outliers. So 65 is where my upper whisker is going to end. And so we're going to put it together and I'll show you what I mean. So I'm going to put all these values in here. So 5, these are all in minutes. My lowest non-outlier value observed, this is also 5 minutes. These absolutely can be the same. Q1 is 15 minutes. My median was at 22.5 minutes. My third quartile was 42.5 minutes. My highest non-outlier value observed, that's this 65 minutes. And then my maximum, which is my largest value, is 85 minutes. So I can use all of this information to put into the box plot. Almost always, the first part of the box plot is going to focus on the box. So Q1 to Q3 is the box itself. The median is the line in the middle, and it doesn't have to be smack in the middle. So I have, here's my number line, and I have a travel time. I probably would even specify it's in minutes. So from 15, honestly, you can make your box plot as tall as you want. It doesn't matter too much. It doesn't mean anything if it's taller or shorter. And it goes to 42.5 minutes. So something like this. Put together, that's my box. So Q1, Q3. My median is 22.5 minutes. So somewhere like that. So this is my median. Next tilde. So things to note here. My minimum value is also the same as my lowest non-outlier value, which is 5. So that's how far the whisker goes out. Here, these two are different. So 65 is where my whisker goes to. 65. But then I still need to include my maximum. It just is its own point. So 85. So like that. So this is my max. This is my min. And this is my largest non-outlier value. It doesn't have a really fancy name that I know of. But yeah, so right here, 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 and here, those are all values from our 5-number summary. So absolutely the 5-number summary, super useful in constructing the box plot. Box plots are a really handy tool for when you have a quantitative variable. We like box plots and histograms when we have large data sets, especially when we have 30 or more. So stem plots we tend to use for smaller data sets, but you can use them for a bigger one. They're just more tedious to make. And then box plots and histograms definitely for the larger data sets. That's definitely preferred. So comparative box plot, we often like to have box plots by groups. So in that scenario where we were looking at rubber seals produced by different machines and looking at the tensile strength, we are going ahead and there are the units for the tensile strength. We're looking at machine 1, machine 2, machine 3, machine 4. Here are my box plots. You can look at like where a lot of times we look for overlap specifically of the boxes. So you see like, oh, well, that machine 4, it seems to overlap most of the machines here. But if you look at machine 3, it really only overlaps machine 4. It doesn't overlap the boxes in machines 1 and 2. That kind of thing. So you would definitely look for like, oh, this, the box part of this plot is a lot higher for this group than that group. You can definitely look at the spread. So if you look at machine 4, it's spread out a lot more than, say, machine 1. So there are a lot of different characteristics you're able to look at. We definitely look for like overlapping versus non-overlapping. That's definitely a major feature we look for. But yeah, absolutely you could compare like, hey, look, Q1 of machine 3 is really, really similar to Q3 of machine 2, that kind of thing, maybe a little bit more, that kind of idea. And then you can see the medians, so a lot of times we would try and compare a lot of times averages between groups, and you might say, hey, look, it's a lot higher for this group than, say, machine 2. So that's just one thing we do to compare box plots. And we'll go back to comparing box plots when we get to the one-factor ANOVA. So onto our code and your turn examples. Strongly recommend looking at them, and we will see you next week.